This is chapter 1.3. We're going to talk about continuity, end behavior, and limits today. Only about half of that today. So the first thing I want to talk about is, what is a continuous function? When you think of something being continuous, it means it doesn't end or doesn't stop, maybe. And the one thing I want you guys to understand, that a continuous function, or for a function to be continuous, doesn't mean it has to go to infinity. As you can see on our diagram here, yes, this has arrows that go to positive infinity, negative infinity, in the x and y direction. That doesn't mean that it has to be that way. It can be a line. It can be a line segment. It can be part of a graph. So graphs can be continuous in parts and not continuous in other parts. But basically, if I'm able to take my pencil and I'm able to draw it without picking up or stopping, that's considered a continuous function. I don't pick up my pencil. I don't have to jump over anything. There's no holes in the graph. Okay? So even a segment from here to there can be considered continuous. Now, a limit. The limit of something is the value a function approaches. Now, when I say approaches, it doesn't have to actually touch. It doesn't have to be there. It's going to be a value that it goes towards. Think of the earliest idea that I can think of limits you guys would have actually had access to would have probably been something like asymptotes. You remember your asymptotes on your graphs? The graph approached it, but it never actually touched it. So therefore, as the graph approaches it, it goes closer and closer. So if you had taken exponential decay problem, they look like this. It's because they approach that imaginary dotted line, right? At x equals 0. The limit of that graph as x goes to infinity, so that means it keeps on going over further and further and further and further off the graph, it's going to get closer and closer and closer and closer to 0. So the limit as x approaches infinity would actually be 0 because it's approaching 0. It doesn't actually have to be there. Okay? The value of the graph to be a limit does not actually have to exist at that particular point. Because you can't exist at infinity, I guess you would say. We can approach infinity, but we can't ever be there, right? Because as soon as you're there, someone else can kind of go a little bit further and a little bit further and a little bit further. So that's what we would say is a limit. It's a value of a function approaches, or that a function approaches. Now, if we're looking here at the key concept stuff, then it says if the value of f of x approaches a unique value L, as x approaches c from each side. So, looking at this really crazy looking chart here, c is right there. That's c. And c in the function goes to this value right here, which is L. Okay? Now, that value of L is what the limit is approaching. Why? Is because there are two different types of limits, we're going to say. There are limits as x approaches c from the negative side, and limits as x approaches c from the positive side. For a limit to exist, those two limits, now granted, guys, we should be putting f of x in here. F of x, because it's the limit of f of x. Those two limits have to be equal for the limit to exist. So, going back to our diagram there, if I let x start way over here at x1, it gives me this weird value that's not even, doesn't even seem like it's close to L yet, right? But look what happens as x starts getting closer and closer to c. The value starts getting closer and closer to L. And if I go right next to it, I go just above. That would be from the negative side, C negative. I can do the same thing on the right side, that if this is x, right here, I can go way over here even. Boom, it go to this value way down over here. That's not L. But as x is getting closer to that C value coming from the positive side, I get a little bit closer, and a little bit closer, and eventually I'll get to the point where it is C, and they actually are approaching the same exact value. Whoop, right there to L, and then from this side, right to L. Okay? Can you guys see it? So the limit from either side has to approach the exact same spot, aka same y value. Yeah? So if we're going to talk about continuity, then we probably should talk about discontinuity. So discontinuity or discontinuous functions are functions that have holes in it. You have to lift your pencil, yes, to get from one side to the other. A lot of the times when I think of discontinuous functions, I'm thinking of those piecewise functions. Because I think most of the time we've ever dealt with piecewise functions, they looked more like this middle graph right here, right? I come in, I got to pick my pencil up and go again. That's a discontinuous function. There are three different types of discontinuity. The first one stated there is infinite discontinuity, which means that as I'm approaching that value of C, the left and right hand limits fly off to infinities. This particular case, one goes to negative infinity, the other one goes to positive infinity. It's okay. That just means that it's discontinuous. They both could technically go to negative infinity. So instead of there, I could have went this way instead of the top. So that's like not there. This would still be discontinuous by infinite discontinuity because they both go to negative infinity. But I can't get from here and then go all the way back up that way. There's no loop right here. There's no loop. It just goes on forever. Okay? So be careful. They don't have to diverge to different infinities. Another one is the jump discontinuity. That's your piecewise idea. That one function goes to the point of C, and then you got to pick up, and then you got to go again. Okay? And the removable discontinuity, that's an interesting one. That's an interesting one because you may have dealt with this already. You may have dealt with this because, what if I asked you this? This is a type of function. It's a rational function because it has a fraction. And if I had to graph this, everybody should know this idea that I cannot put what into this function. What's not allowed to go in? 2. A 2 because it can't divide by 0. There should be a vertical asymptote at 2. But here's the thing. If I wanted to graph this, wait, does anybody recognize that that top is a quadratic, but it's a special one? Can't I factor that? What is the top factor to? X plus 2 and x minus 2? Wait a minute, what happens to the x minus 2's? They cancel, aka remove each other. So all I'm doing is graphing x plus 2, and x plus 2 is a line. But here's the thing. If x plus 2 is a line, and a line says, hey, I can put any x value I want in, great. That's easy enough to graph. But we still have to honor the fact that in the beginning, the function was this, and it said we could not put in what value? 2. Look at our graph here. This is just an example. It fits kind of nicely. If I let C be 2, there would have to be a hole there. It can be every value but 2. So it creates a hole, you jump over the hole, and you keep going. But here's the thing. It's been removed, the asymptote, and created a hole. That's removable discontinuity. The function is continuous everywhere except for at C. Notice that it's continuous everywhere else. If I wanted to know, is it continuous over here? You would say, yeah. Is it continuous over, nope, not that big. Over this side? Yeah. But is it continuous in the middle? No, because I had to pick up my pencil. Cool? So now let's talk about the continuity. So the non-removable discontinuities are those first two graphs. So let's talk about the continuity test. The continuity test works just like if I was checking my system to see if a point is a solution. If I said, hey guys, this point is a solution to the system, can you check it for me? You put it into the first equation, and if it works, you got to try the next equation, right? And so on, however many equations there are. If you get to that first equation and it doesn't work, do you keep going? No, you stop. Your work has been done. You proved it wrong, you don't need to keep checking. Same thing with the continuity test. There are 3 tests. The 3 tests are that if a function f of x is to be continuous at x equals c, then it satisfies the following conditions, and all 3 have to be satisfied. First one, f of x is defined at c, which means when you put c into the function, whatever it is, you get a value that's spit back at you. So if you put 2 in, you get a value of 10. Hey, I'm good. Part A exists. We're moving on. Part 2 says that the f of x approaches the same value from either side of c, aka the limit as x approaches c of f of x exists. Means the left-hand side and the right-hand side go to the same value. And then part C, or part 3, says that the value of the function that the function approaches from each side is the same as the value of the function. Steps 1 and 2 have to be equal. The value has to exist, the limit has to exist, and to tie it all together, they have to be the same. And if all 3 of those conditions are true, then it's continuous. If any one of those gets a no, it's not continuous, it's discontinuous. Okay? So, look at your problems there. F of x equals x cubed is the first one. I want you guys to determine whether the function is continuous at x equals 0, justify using the continuity test. Now there's a couple ways to do this. I think the easiest way to do this is to make a graph. Take out your graphing calculator and actually graph y equals x to the 3rd power. So we take the time, we make that happen, and hopefully everybody says, wait a minute, I know what that graph is. Kind of looks something like that. There's supposed to be an arrow down there. Okay. So everybody get the graphic calculator out, verify that real quick. But that's what you see. Step number 1 says that f of 0 should exist. What is f of 0? That's 0 cubed, which is 0. So, does f of 0 exist? Yes. Step 2 says the limit as x approaches 0 from the negative side of the function should equal the limit as x approaches 0 from the positive side of f of x. AKA the limit should exist. Well, let's go from the negative side. As x gets smaller and smaller, or bigger and bigger, I guess, going towards 0, right? Less negative. The graph is going towards what at 0? The value is approaching 0. Wait a minute, check the right side limit. As x gets smaller and smaller and smaller and smaller and smaller, it approaches 0. Now remember, sorry, when I say, I can't say it's getting smaller, I say it's approaching 0. So it gets closer and closer and closer to 0, it is getting to be 0. So the limits equal 0, which means that the limit exists. Step number 3 says, are these the same? So therefore, it's a continuous graph. Yeah, that's all we have to do. Part B, do the exact same thing. This one's a piecewise function. Determine if it passes the continuity test. I'll give you guys some time. Question. Does f of 0 exist? Which function do I have to put 0 in? Top or bottom? Bottom, because the domain says that it's equal to 0. So I got to put it into the bottom. The bottom is just x, so it means it's just 0. So f of 0 is 0. Now, for this to be correct, I have to approach 0 as a limit. Yes? So, I put this on my graphing calculator. Might be a little more difficult, because how do you put this idea that x is less than 0 or x is greater than or equal to 0? Well, first of all, the bottom one is a line, x. It's 1x. It's 1x plus 0. So it starts at 0 and goes upward if it's greater than 0. So this one should be like this. But what is 1 over x? 1 over x is a hyperbola, isn't it? Which really should be like this. But should I have both sides? No. I only are supposed to take the x values that are less than 0. So I'm going to back away the right side. So that's what your graph should look like. You have to use inequalities or intervals. It matters if you're using Desmos or your graphing calculator. Can you guys see that at 0, does a limit exist? Does the limit as x approaches 0 from the negative side equal the limit as x approaches 0 from the positive side?
No.
Are they the same?
No.
Well, look, from the positive side, it's going to approach 0. But from the negative side, it approaches negative infinity. Is negative infinity equal to 0?
No.
So the limit does not exist. So limit does not exist, therefore discontinuous. I don't have to test anymore. Now, what happens if I don't have a calculator, don't know how to put this on a calculator? What's the backup? If I have to approach 0, guess what I'm going to make? I'm going to make a t-chart. I'm going to make a t-chart for the left side, I'm going to make a t-chart for the right side, and I'm going to put values in and make them closer and closer and closer and closer to 0. So, looking over at that right graph, I can make a t-chart for the left and for the right. And so x will be here. I'll start at something like -1, -1/2, negative 1/4, negative 1/8. And as I get closer and closer down that list, the value starts getting closer and closer to 0. I start on the list on the other side. I'm going to start at 1, then go to 1/2, 1/4, 1/64. And as I get closer down this list, it gets closer and closer to 0. It's going to approach 0. So therefore, you can actually say that the limit, the left-hand side and the right-hand side, can be the same. So default to a calculator to figure out the graphs and make one on your paper. Give me a sketch. Default back, if you don't have one, to making tables to test them. And the last thing for today is determine whether each function is continuous at the given x values. Justify using the continuity test. If discontinuous, identify the type. Is it infinite, jump, or removable? So the first graph is a what? The first one is 1 over x squared. If you guys put that on a graph, what does it look like? It's a hyperbola again. So this is what a graph looks like. Has everybody got that? Now, it says justify using the continuity test. Well, first of all, I don't think I even had to draw anything if I just would have went straight to number 1 and I said, hey, is the graph even defined at 0? 1 over 0 squared. Guys, does f of 0 exist? Can I put 0 in the denominator?
No.
No. So it's undefined. Therefore, it's not continuous. Now, the graph would be helpful because now I can at least look at the graph and say, what kind of discontinuity is that? Is it removable? Is there a hole in the graph? No. Is it jumping from one to the other? No. Are they going to infinity? So this is an infinite discontinuity. The next one's an interesting one. First of all, is it defined at 2? Here's 2. Is it defined at 2? According to this, I need to place it into the bottom function, which is 2 minus 2. So f of 2 is 0. It's defined. We're good. But now we have to go into that limit stuff. And again, if I'm going to do a limit, I'd rather make a graph. Do you guys remember how to do piecewise functions?
No.
I'm making a dotted line at 2. Why would I make a dotted line at 2? What happens at 2? Right. Something happens here at 2 is that that domain changes. Things are happening. This is where one graph starts and the other one stops. Remember, piecewise functions. Things happen on this side independently of the things on this side. They got to pass a baton between each other. So this graph will do its thing, and it'll stop, pass the baton, the other guy jumps in and goes. Right? Now, I almost say that almost 99% of the time, piecewise functions, when we've dealt with them so far, have never met in the exact same spot, even though I think we've all done piecewise functions where they meet and stop, start and stop at the exact same point. Those can be considered continuous. And so, we got to graph this. Which function goes on the left side? Top one or bottom one? left side. Left side are the negative or less than values. That would be the bottom one. So this one says starts at 2 and the slope is negative 1. 1, 2, so down 1 over 1, so it's that. The other one is a line as well, but it starts at 4 and goes up 5 over 1, up 5 over 1. But the problem is that if I started at 4 here, I'm not actually here. I can't be, because the graph doesn't exist here yet. It only exists on that side. So what we could do is you can graph the whole line and erase half, or you can start at 2 and go to 3, 4, 5 and make kind of like a table. So what happens when I put 2 in here? 2 times 5 plus 4 is like 14, right? So it's an open dot. And then it's going to go up 5 over 1. Up 5 over 1. It's going to go there. Is this a continuous, smooth curve? No, because I'll be going here, going here, going here, going here, and then stop, jump, and on. So this is discontinuous by what kind of discontinuity? Jump. Bless you. Homework for day 1 is 1.3, page 30, 1 through 10. Have a great day.